All right, so now we're going to go through a new chapter, essentially discussing technology. So far, we have discussed enough steps to understand that we need to build resonators and we need to build coupling sections or inverters in our filter. This is really the bread and butter of a filter, coupling sections and resonators. Typically, the coupling sections are far easier to design than the resonator, so we're actually going to spend a little bit of time discussing technology options we have for resonators. My goal here is not to give you an exhaustive list, but rather tune your mind and sharpen your mind to the point that you can choose, you can make rather an intelligent choice for the frequency range that you're designing for. So first of all, I want to remind you some important definitions here and perhaps clarify some of those that you may have heard in different ways. So the most important number that we can essentially assign to a resonator to judge its quality is basically the quality factor. And so the quality factor is a metric that links how well this resonator stores energy versus how well it dissipates it. Of course, in reality, you want a resonator that stores energy really well and doesn't dissipate it at all. Something like this cannot happen, and so we define this quality factor. Now, before I give you the precise definition of the quality factor, I want to acknowledge that most likely you have seen quality factor defined in a different way, particularly if you're fairly new to the filter design. For example, most undergraduate textbooks will basically give you a filter curve like the one that you see right here, and they will very simply say, well, the quality factor is nothing else but the frequency of the filter divided by its bandwidth. And so essentially they will go ahead, they will find the center frequency of the filter, they will basically find perhaps the 3 dB bandwidth or the 1 dB bandwidth, depending on how you want to divide it. They will basically divide the two and they will give you a number. As we will see, this is a useful number, but it's not the quality factor that I am talking about here. In fact, this will be called the loaded quality factor. And what we really need to find out, and we will define precisely, is the unloaded quality factor. So keep that in mind as we're basically starting this discussion. There is also the shape factor of the filter, which sometimes is being confused with a quality factor. And I want to remind you that the shape factor of the filter is nothing else except how sharply your filter ejects once you move away from its passband. So the shape factor is, in other words, something related to the order of the filter N. And even though it is loosely connected to the quality factor, meaning the losses of the filter, that's not basically what we're talking about here. We'll discuss later on in more detail that how the losses of the filter may actually affect your ejection. So let me give you a reminder, first of all, of the true definition of the unloaded quality factor, which is basically the quality factor we're talking about here. So as I mentioned before, and the equation is right here, the unloaded quality factor is basically related to the energy that you're storing in the resonator over the energy that you're losing from the resonator. Where are you storing energy and where are you losing energy? So energy is actually stored in the volume that you have available for your electromagnetic field. In general, the larger the volume you allow for the resonator, the larger the volume will be for storing energy. And so in general, maximizing the quality factor, unfortunately, means maximizing its volume. So that's a general principle. The more volume you have, the better the quality of your resonator will be. Or conversely, when you try to tightly pack things, you lose in quality. Now, where is energy lost? There are actually three main factors that contribute to energy loss. The first one is the metals that you have. No metal is ideal. You will always have ohmic loss. So if you want to avoid losses as much as possible, limit the amount of metal that you have. The second is lossy dielectrics. If the electromagnetic fields are stored in a large volume, but all of this volume is taken by a dielectric that consumes energy, then it's reasonable to expect that you will have a low quality factor. Finally, something a little bit forgotten often is radiation. That's particularly of concern when we're talking about high frequency designs. Unfortunately, fields tend to radiate away from the structures that are holding them, And a lot of times, designing for low ohmic loss may actually lead to high radiation. For example, wide transmission lines, tend to have lower losses than narrow transmission lines. While wide lines also tend to radiate fields more than narrow transmission lines, and so that three may actually compete with one, depending, of course, on what your frequency range might be. Now, how can you actually tell that your quality factor is sufficient or insufficient for your filter design? So let's go back to the curve that most of us are accustomed of looking at and essentially make this important link between unloaded quality factor, which again is a metric for the resonator itself, versus what you will actually see in the lab, versus what you will see when you measure the filter. So the most important thing that you will actually notice is the insertion loss of your filter. So the insertion loss is basically the loss that you will have in the passband of the filter. What is really important to keep in mind here is that the worse your quality factor is for the resonator, the worse the insertion loss will become. So these are two interesting lines. Actually, it's two interesting cases. One is for a 3-pole Chebyshev filter. The other is for a 4-pole Chebyshev filter. And each one gives you the actual shape of the filter when the filter is built with resonators whose quality factors is degrading from 800 down to 100. So what you can notice very clearly here is that if you can build this filter by employing resonators with a quality factor of 800, then your insertion loss might be only something in the order of less than a dB for here and even less for here. You know, that's great. That's typically the type of insertion loss that we want to see. And in fact, the less insertion loss, the better the system will be. You know, go back to your system level design and recall and remind yourselves that this insertion loss of the very first front-end filter directly impacts noise figure. But now, if you're limited with a quality factor of a resonator to be only of 100, suddenly the loss here will jump to something in the order of 6 dB. For most practical applications, that filter is actually unusable. For most cases, having a 6 dB insertion loss for the front end is basically a pretty bad choice. So the first lesson from these curves is that there is a limit of how bad of a resonator you can tolerate. So if you said, for example, that my insertion loss, let's say, has to be at most 3 dBs, then that means that for this case, for the 3-port Chebyshev filter, you can tolerate a resonator that has an unloaded Q of 200 and above. You can't get basically anything else. The second lesson that these curves can actually teach us is that broadband filters are more forgiving than narrowband filters. So here's an example. This 4-pole filter has an 8% bandwidth, while this 3-pole filter has a 3% bandwidth. So even though the design here is a 4-pole filter, which in general it means that this should have higher loss than a 3-pole. You know, the more poles, the more resonators you are, the higher the loss of the filter in general will be. Because this filter is so broadband compared to this one, its insertion loss is actually lower for a given quality factor. And so, for example, look at the case for Q of 100. The narrowband filter has about 6 dB of loss. This guy here has less than 5 dB of loss. So again, broadband filters tend to be more forgiving than narrowband filters. So if you can afford a wideband filter, definitely go for it. In real life, the bandwidth of that first front-end filter is actually dictated primarily by the specs of the system. So you may or may not have much flexibility there. But the truth of the matter is that you can tolerate a worse resonator, a resonator with lower unloaded Q, if you have a wideband filter. Now, in the literature, you can actually find equations like this one here that will actually give you a fairly good approximation and a fairly good first estimate before you even design the filter in terms of insertion loss, which is this number here, and unloaded quality factor, which is this number here. There is this coefficient Cn that you will see in this equation, which is basically a coefficient that depends on the exact filter you're designing. For example, a Chebyshev coefficient will be different than a Butterworth one. And so you can find those in tables. And so the amazingly useful thing of this equation is that you can actually get a pretty realistic estimate for your unloaded quality factor. And I'll show you later on some examples regarding this part. Now, this graph here, I'm going to go very quickly, but essentially it shows exactly the same thing that we discussed so far. It basically plots the insertion loss of the filter as a function of the unloaded quality factor for a few different cases. So first, you can see that there are two sets of lines. One is for a 3-pole, the other is for a 4-pole. The lines with the dots are for the 4-pole. And then you can also see that we're plotting for filters of different bandwidths. And so here you can see the dramatic difference that the bandwidth makes in terms of insertion loss. For example, if my unloaded quality factor is 300 and my, let's say, 3% filter is up here, you can essentially see where the 6% filter is and where the 12% filter is, each one yielding basically lower loss the more wideband you make the filter.